Hi, welcome to UMP STEM Lab program. We are delighted to be part of your learning experience. As much as we enjoy our daily routine in engineering education ecosystem, we are also keen to be part of the STEM community. We look forward to bring engineering to the young generation, the school children. UMP STEM Lab also offers digital making classes with one ultimate motivation: to expose the teachers and young school children to the fascinating world of engineering. We strongly believe that early exposure will ignite interest among the youngsters to take up STEM in their future, inshallah. Digital making skill sets curriculum in UMP STEM Lab comprises of 4 main elements. Design, the skill to sketch and design 2D and 3D shapes in complete finished projects. Programming, the skill to code basic, abstraction and higher order instructions. Manufacturing, the ability to create basic prototypes and advances into completed projects. And physical computing, the skill to develop basic electromechanical and later advances to automated systems. For this year, Digital Ninja Accelerator Lab 2020 technical module consists of Arduino Robotics for the fundamentals, Rapid Prototyping for Intermediate 1, and Raspberry Pi IoT for Intermediate 2. In this session, we will be focusing on fundamental Arduino Robotics module. In the fundamental module, we will be utilizing UMP STEMBot as our learning platform, targeting the following outcomes: physical computing, electronic systems and Arduino microcontrollers, in which we will look into basic interactions between digital and analog sensors, signals, display, actuators, and electromechanical system with motors. Whereas for Arduino programming, we will look into C++ based programming concepts. Included in this module is basic skills in sequential, conditional, and iterative programming concepts. We will then advance into autonomous programming applications. These two skills are essential in digital making process that offers the participants the ability to make a working prototype in their innovation projects. By now, I believe you should receive your STEMBot kit. Now, let's unbox your STEMBot kit. Your STEMBot should consist of the UMP STEMBot, a lithium-ion battery, a lithium-ion charger, a mini USB cable, an Arduino Nano, an ultrasonic sensor, and a learning module. The STEMBot here comprises of 2 units, which are the control board and the power board. Now, let's have a look onto the control board. The control board is equipped with an OLED display, LEDs, Bluetooth sensor, and 3-axis gyroscope and accelerometer. There are also connections spared for ultrasonic sensors and auxiliary sensors output. As shown here, the board is also equipped with an MPU 6050 3-axis accelerometer and gyroscope chip. The gyroscope chip measures the rotational velocity, which is the rate of change of the angular position over time, along X, Y, and Z axis. Whereas, the 3-axis accelerometer measures both static and dynamic forces of the acceleration. The Earth's gravitational force is a typical example of static force, while dynamic forces can be caused by vibrations, movements, and so on. So, when combined, it can measure gravitational acceleration along 3 axes. And using some trigonometry mathematics, we can calculate the angle at which the sensor is positioned. So if we fuse or combine the accelerometer and gyroscope data, we can get very accurate information about the sensor orientation. The Bluetooth sensor enables the UMP STEMBot to be controlled remotely using open source platforms such as MIT App Inventor, students can develop Android-based applications, such as shown here, to control the robot remotely. Details of this can be found in the electronic system, the robot, and the applications book. Another unit of the STEM board is the power board, which houses the battery holder, a pair of micro DC motor, and tires. The limitation speed of the robot depend on the properties of these micromotors, which is typically called as RPM or revolution per minute. These can be easily upgraded. As mentioned earlier, UMP STEM Lab views one critical aspect of digital making skill is physical computing. Physical computing involves interaction system that can sense and respond to the world around them. In a nutshell, information are retrieved from the environment through sensors, processed, and later interact with the environment via actuators. Signals to and from physical computing system generally can be divided into analog and digital signals. UMP STEM board is based on the Arduino Nano technology. This is a diagram of the Arduino Nano. There are altogether 30 pins. The 16 MHz 8-bit Atmega 328 microcontroller is the heart of the Arduino Nano development board. In the center of the board is the physical reset pin. The LED indicates the communication between the board and a computer, as well as its power status. Programs and codes are uploaded to the board via a mini USB jack. V-in pin is reserved for input voltage to Arduino, while an external power source 6 to 12 volt is used. And the ground pin is used to complete electronic circuit. Arduino Nano has 8 analog input pins, which is used to measure analog voltage in the range of 0 to 5 volts. Digital pins D0 until D13 are used as input or output pin, 0 volt for low and 5 volt for high. Note that pin 3, 5, 6, 9, 11 with sinusoidal symbols denotes that the pulse width modulation properties of the output. For Arduino Nano, these pins are 8-bit PWM output. Throughout this course, we will go through activities that involves programming the Arduino on the STEM board to interact with sensors and actuators. Activity 1 and 2 involves LED to be programmed via digital output. In Activity 3, the programming involves infrared sensors, or typically known as IR sensor, which are located beneath the control board as shown here. The infrared transmitter transmits infrared radiation, while the IR receivers collect the reflected radiation. Dark surfaces generally are better absorbers compared to the fair surfaces and display higher readings. With the input from IR sensors, the STEM board can be programmed to react upon different surface colors. Here, students will also be introduced to serial monitors as a diagnostic tool in programming and troubleshooting the STEM board. Sequential-based programming skills are mainly involved in these activities. Activity 4 progress to conditional statements in programming, which involves if statements, if-else statements, and nested if statements. Here, participants get to code the Arduino output to react upon certain input criteria and threshold values. Arduino is an open source platform, and there are numerous resources available online. To do so, students must be able to add in modules or libraries to the existing projects. Activity 5 in particular focuses on adding libraries to the program. In this case, the organic LED, also known as the OLED. In Activity 6, participants get to program the ultrasonic sensor to estimate distance. Among applications that uses this concept is in obstacle avoidance robots or devices. Activities 7, 8, and 9 will make use of the power board, in which involves the STEM board to be programmed as a line-following robots. Activity 7 focuses on programming the STEM board to a predefined route. It begins with the simple forward and reverse functions, followed by right and left turns, and finally timed movement. Here, the programming involves iterative statements. Both Activity 8 and 9 involves building functions to program the STEM board to react upon the IR sensor readings for the line-following robots applications. Together with me are Kamil, Pua, Chishun, Shafiq, Faiz, Zulamil, Amirul, Natalie, and Shahmi. They are the mentors of UMP STEM Lab who will guide you along the learning process. I wish you all the best and hope you'll enjoy this session. Thank you.